Okay, we're back. This is just some kind of like, just some things to note about how implicit differentiation works. The derivative with respect to y of sine y is cosine y. And I don't have to worry about the derivative of y here because this variable here with respect to y matches the variable here. And so there's no y priming that has to be done when these things match. But this one is derivative with respect to x of sine y. So that's going to be cosine y times y prime. Or, as we saw before, you could write as cosine y times dy dx. And this happens because this x and that y does not match. That's why this thing has to appear. You could think of this one as like you multiplied, you did cosine of y here because that's the rule, then times the derivative of y. But derivative of y with respect to y is 1. So like the y prime here is always equal to 1. In this case, the derivative is taken with respect to x, and this is not an x. Not an x. That means I have to do this. I have to add this y prime or else I'm not doing it right. So similarly, this is just another example of that. The derivative with respect to y of y to the fourth is going to be 4y cubed. And again, because this y matches that y, I don't have to worry about implicit. In some sense, I'm multiplying by the derivative of y, but that with respect to y is equal to 1. This is the other situation where this x and this y do not match. This is not y. This is not x. This is y. So since these don't match, I do the rule like I did before. But then I got to multiply by the derivative of y with respect to x. And like you think of this y to the fourth as being the inside function. Think about it like this, maybe. It's like some function of x to the fourth power. And you know from the chain rule that this is 4 f of x cubed times f prime of x. The chain rule, right? The f of x is some function. I don't know what it is. Y and f of x in many senses are the same thing. So that's kind of how we're looking at them. So this f prime is the same as this dy dx. So that's how this works. There's some more examples. We'll come back to that in a second. All right, let's do a couple of these. So this is a product here, x times y. So I got to do the product rule. I do the derivative of the first thing, which is 1 times the second thing, which is y, plus the derivative of the second thing. And the derivative of this is y prime. The derivative of y with respect to x is the derivative of y with respect to x times the first thing. So this is dy dx. You can think of it like the derivative. If this was x, the derivative would be 1, and then times the derivative of y, which is this. So it's really 1 times dy dx times x. So remember, this is just the product rule. Derivative of the first times the second, plus the derivative of the second thing times the first. We can do the same thing here. It's like a little trickier in this one because you can see the variable I'm thinking about here is t. And so these t's are going to act like x's normally would because it's with respect to t. But this y, I got to think about that as a function of t. I don't know if it's a function of t or not, so I have to assume that it is. So I use the quotient rule because this is a quotient. Derivative of the top is 2t times the bottom, which is y, minus the derivative of the bottom, which is dy dx, or sorry, dy dt in this case, because the independent variable is t, times the top, which is t squared, and the bottom is the bottom thing squared, which is y squared. So again, this derivative with respect to t of y is always going to be dy dt. It might be a more complicated function than just y. We saw that up here. Nope, up here. This was y cubed, so it's 3y squared times the derivative, and this was y squared, so it was 2y times the derivative. But if the function is just y, then its derivative is just dy dx or dy dt, depending on what the variable is. So here we go. This one's like a little more typical of what we might expect to see on, say, an AP test or on one of my tests. So we're going to do the derivative with respect to x of both sides of this thing. 3y cubed plus x squared. The derivative with respect to x of 5. So this is now this implicit situation where I have an x here and a y there. So I got to do the rule, the normal rule, which is 3 times y squared, but this 3 out here is going to give me 9 y squared. Then I got to do this y prime thing. This is implicit differentiation. This is the whole point of what we're doing now. It's a little bit different, but not usually so. The derivative of this is 2x. I don't have to use implicit because this x matches that x. The derivative on this side is just 0. And now I'm going to collect all the y prime terms on the left and all the non-y prime terms on the right. So I subtract 2x from both sides. And I get 9y squared. I'll write it as dy dx because that's what the problem said. Equals negative 2x. Now I divide both sides by this 9y squared. I get dy dx equals negative 2x over 9y squared. And that's how this works. We found dy dx. We did it. Go us. This is basically the same thing, a little bit different. You might want to consider rewriting that that 1 over y is y to the negative 1 because it might help you take the derivative, but it's not that vastly important, but we probably will. So let's say this is y plus y to the negative 1 equals x squared plus x. I'm going to take the derivative with respect to x of both sides. Y plus y to the negative 1 equals with respect to x of x squared plus x. The derivative with respect to x of y is dy dx. The derivative of this one, I got to use the rule here, which is negative 1y to the negative 2. Negative y to the negative 2. And then because this does not match that, I got to multiply by the derivative. Another dy dx appears. And now the derivative with respect to x of x squared is 2x. No chain rule or implicit needed because this is an x. And then derivative with respect to x of x is 1, so I get a plus 1. And now I'm going to rewrite this so it's a little neater. Dy dx minus y to the negative 2 dy dx equals 2x plus 1. Now I'm going to factor the dy dx's out here. So I get dy dx times, factor it out of this, I get a 1. And then I factor out of this, I get minus y to the negative 2 equals 2x plus 1. Now I divide both sides by this thing. I'm left on the left side with just dy dx. And on the right side, I have 2x plus 1 over 1 minus y to the negative 2. So I've now found dy dx as requested. A couple more things just to kind of finish up here. Remember our first, like the problem that kind of inspired this new technique was to find the equation of a tangent line to this graph at that point. So now we maybe can figure out how to do this. We're like, well, this is a point, and since this thing has y's in it, it can't be solved for y. I'm going to have to use implicit differentiation to find dy dx. So remember, it's the equation of a tangent line, which you've done a million times. We need two things. We need a point and a slope. The point we're given. The point is 4, 3. The slope is going to be a little trickier because we're going to have to do all this implicit shenanigans. So let's do that though. So we're going to derivative with respect to x of both sides of this thing. So I'm just going to write it. This is a little bit funky notation-wise, but it takes less writing, so I'm going to do it. Instead of writing that d over dx twice, I'm just writing derivative with respect to x of this whole equation. That's what this means. It's what I did before. It means this side and that side. So my first term is x squared. Its derivative with respect to x is 2x. My second term is y squared. Its derivative with respect to x is 2y times y prime. You use the same rule as I did here, 2 times the thing to the first, times the derivative of the thing on the inside. Then the derivative with respect to x of 25 is 0. So now I want to get all my y prime terms on the left and all the other terms on the right. The side doesn't really matter, but normally we solve things this way. I subtract 2x from both sides. There's nothing to factor here because there's only one term. I just divide both sides by 2y. This cancels out, and I'm left with y prime equals, the 2's cancel out 2. I'm left with negative x over y. What this tells me is that the slope of the tangent line to this graph for any value of x and y is always negative x over y. So like if I was talking about this point, which is looks like the point -5, 0, I'd plug in -5 for x and 0 for y, and you can see that that would give me an undefined slope. Like it'd be 0 on the bottom. If like let's say I'm choosing this point, which is -5, 0. If I plug that in here, if I plugged this point into this slope, I would get -5 over 0. And while these cancel out, it doesn't really matter because the 0 on the bottom tells me that there's no slope there. It really doesn't tell me there's no slope. It tells me that the slope there is undefined. And you can maybe see that that's going to be the case because the tangent line there is vertical. And we know, hopefully, we remember that vertical lines have no slope. They have an undefined slope. And that's what this means. It means that it's a vertical line. On the other hand, if I took this point at the very top, you can maybe guess the tangent line there is going to be horizontal, something like that. So I would expect the slope there to be 0. And that point is the point 0, 5. And if I plug that into my slope, the derivative I found here, I get -0 over 5, which is 0, like I hoped. And here I have this point. I would expect that slope to be like somewhere between -1 and -2, maybe. That would be my guess. I don't know. So we don't have to guess though, because we know we have the x is 4 and the y is 3. So y prime at the point 4, 3 is negative the x coordinate, which is 4, over the y coordinate, which is 3, -4/3. That's my slope. And I had a point, the point was 4, 3. So now I do y minus 3 equals -4/3 x minus 4. Did I do that right? Yeah, 4 for x and 3 for y and -4/3. So this is now the equation of that tangent line. So that was the point of this. We can now find this equations of tangent lines to curves that are not functions of x. And that was the whole point of this. So what, right? Who gives a crap? Reasonable question. This is what we just did. Find slopes of tangents to curves if they're not functions. Here's an example. X plus 1 squared plus y minus 2 squared equals 20. That's this weird looking thing. It's a circle. Center is -1, 2, and the radius is the square root of 20. And we could find the slope of the tangent line to this curve. If we could find the equation of the tangent line, we could find the slope, we could find it all. We could find the slope of the tangent, we could find the equation of the tangent line. That was a lot of talking. And we do it by doing implicit differentiation. I'm not going to do this problem right now, but we could if we wanted to. We do it just like we did the last one. Another thing we can do, and this I am going to do, is we can take second derivatives like a boss. So given this thing, find the second derivative. This means the second derivative. This one, we already found the first derivative, so I'm going to cheat and just start there. But normally you would just take the first derivative like we did right here. And we ended up with -x over y for the derivative. So dy dx is -x over y. Now the second derivative means take the derivative of this thing. The derivative of with respect to x of that thing. So this is a quotient of x and y, or -x and y, if I want to think about it that way. And so I can do its derivative by using the quotient rule. So the quotient rule says derivative of the top. I'm just going to call the top -x to make this a little bit easier. Actually, I'm not. I'm just going to say negative. The negative just kind of comes along for the ride. I'll put it out front. So negative, and then the derivative of the top is 1 times y minus the derivative of the bottom, which is y prime, times the top, all over the bottom squared. That's y squared. And that's great, except for one thing. We don't like for the second derivative to have a derivative in it. I want this second derivative in terms of x and y, not in terms of x and y prime. So like, how do I get rid of this y prime? Well, I actually already know this is y prime. It's right there. That's y prime in terms of x and y. I already found it when I did the first derivative. This is the first derivative. This is the first derivative. That means I can replace this y prime with this negative x over y. So we would write negative 1 times y is just y minus, and instead of y prime here, I can write negative x over y. So that negative and that negative is going to make this a plus. It's x over y, so it's going to be x squared over y, all over y squared. All I did here was I replaced this thing with negative x over y, because that is y prime. All right, this is y prime, that's y prime. I can just replace this. X over y times x is x squared over y, and the two negatives cancel out and made it positive. And so this is now my second derivative, d squared y on dx squared. And that's what we use implicit differentiation for. We're going to see moving forward a bunch of different kinds of ways that the AP test, and I will be assessing you guys on this. So keep an eye out for all that. Bye.